So I'm here to talk to you about the US Animal Movement Model, USAMM, Bayesian approach to modeling a partially observed continental scale livestock movement network. Computer simulations can be a valuable tool when trying to model the outbreak of FMD, and it can help us to localize hotspots. We can, through simulations, evaluate control strategies such as movement bans and culling and vaccination strategies, and it allows us to inform policy regarding preventive actions. And in case of an outbreak, animal transports will be important, especially during the silent phase. And in the EU, legislation requires that electronically records of cattle transports are kept. In the USA, that's not the case, but they do however have this Interstate certificate of veterinary inspection, which is like a certificate issued whenever a transport is leaving a state. So the key word here is interstate. We have obtained a 10% digitalized sample of these ICVIs, and that is roughly 19,000 transports. From this, we set up a transport network where we use the nodes. We use nodes as the US counties, and cattle transports are the edges. Now we've put it into a parameterized kernel model that helped us to describe the underlying process behind this network. And from the estimated parameters, we are going to generate new complete networks, and that is 100% networks. That is 100% of the out-of-state shipments, and as well as the intrastate shipments. So in USAMM and in USAMM version 1, which by Instrumental 2013, we used the 10% ICVI data, and we used the number of farms in each county, and we used the historical inflow to a state to estimate parameters that can give us the 100% network. So we put this data into a hierarchical Bayesian framework, and we use Monte Carlo, market chain Monte Carlo techniques to estimate parameters, and we estimate parameter distributions. And by generating new networks from parameter distributions instead of just maximum likelihood estimations, we can take uncertainty into account in our predictions. And the distance, the probability of a transport is distance dependent. So we use this displacement kernel, an exponentially decreasing function with d. We have the distance between counties, and A and B are the parameters to be estimated. And these are, in fact, we get distributions of these parameters. And here you can see just different kernel shapes for 3 different values of A and B. So it's a conceptual figure we find. Here you can see the tail of the kernel. It's just to show you the flexibility of this kind of kernel. I should also mention that these transport probabilities are relative. So the probability of a transport is not only dependent on the absolute distance to the farm, but also on the distance to all the other farms where the transport could have gone to. If you look at the intrastate estimation, works something like this. So we use the interstate transports and the kernel to estimate the intrastate transports, which we have not observed. So we look at county 4 in state B. We observe movements to county 1, 2, 3 in state A, and 7, 8, 9 in state C. And here the heights of the bars are proportional to the number of movement. So from the observed movements, we fit the kernel parameters, and then we get the kernel here drawn in blue. So from the kernel we can estimate within state shipments. So in the first version of the USAMM, it uses a state-specific kernel estimates, state-specific A's and B's, and it estimates the number of transports that's going out of the state, and to generate to the full networks in the end. This is extended in the USAMM version 2 model, but we can look here first at the USAMM version 1. So we have the observed network to the left, generated to the right, and you can see that the overall structure is captured very well. So here are networks for 3 different states. USAMM version 1 does well when it comes to the different network measures. For instance, the betweenness score. If you look at the betweenness distribution, you can see here the randomly generated networks, drawn in gray. You see the data, the observed betweenness distribution in red, and then the USAMM version 1 generated networks in black. And they do match with observed. There are some drawbacks though. USAMM version 1 underestimates the number of counties with many transports, and it lacks, it has no seasonality included, and it also lacks additional information on the infrastructure that can be explained explaining the contact patterns. So in USAMM version 2, we do our estimations at a quarter of a year basis. And to that, we add 3 different things, and we're going to look at the result after we added each of these things. So in fact, we got 3 different versions of version 2. Here, first off, we estimate the attraction parameter, which is basically the historical inflow. So instead of using a fixed number to each state, we're using quarterly estimates instead of the attraction for a farm in a given state. And we also add this extra information, extra covariates on different. It's different data, and it's like we have proximity to slaughter, we have a number of feedlots, and the market volume, for instance, which can explain the movement pattern. And then we add what we call super nodes. So we look at the 10% nodes with the highest in and out degree are given an extra parameter to be estimated, and this will help us to address the problem with underestimating the number of counties with many transports. So, as I told you, we got 3 versions of the version 2. We have basically the USAMM version 1 plus the attraction parameters. So we said no covariate model. We get the attraction plus additional covariates, and then on top of that we add the super nodes. So if we look how well we're doing with the USAMM version 2, we can look at them, for instance, the maximum degree. So here you have maximum degree on the x-axis, and on the y-axis you have the frequency. So this is for 1,000 generated networks, the maximum degree from 1,000 generated networks in each model. So you have the model column-wise, and you have in degree on the top and out degree in the bottom. So in the red line are the maximum degrees taken from the data. So we do underestimate when we use no covariates. We overestimate when using covariates only, but we capture the maximum degree distribution quite well. We captured the maximum degree quite well when we use the most complex model. Further, if we look at the degree distribution in total, you see here again the 3 models column-wise, in degree on top, out degree on the bottom, and you see the density and the degree. So if you look at from 10 degrees and upwards, we're doing far better job, especially on the out degree, to capture the degrees of distribution when we use the most complex model compared to the simpler model. And we can further look at the out degree on a state and quarter basis. And we see that basically the data, and this is the median out degree of 1,000 generated networks. So, and the colors correspond to the log degree. We see that the data and the generated networks, they match. And we can see that there are large differences between the states, but the seasonal effects are not as large as we anticipated. The same conclusion holds for the in degree. It matches data and the generated networks. We have large between states differences, of course, and we get smaller between quarter differences in degree. And here is an example of USAMM version 1 put into a visualization software written in the R package Shiny. So you can choose your focal county or focal state and see how that affects its role in this network. So to summarize, the USAMM version 2, especially the most complex model, gives us a better prediction of the maximum degrees. It gives us a better prediction of degree distributions, and especially on highly and medium connected nodes. And these would probably be the most important in the case of an outbreak. And it captures the overall in and out degree quite well on the state and quarter level. And also that the seasonal effects were a bit less than we anticipated. Thank you for listening.
Thank you for this presentation. Are there questions for Peter? If not, I might have one. So, how can these results help policymakers to decide what measures to apply in case of an outbreak of EuFMD?
Well, because these results are basically, you have this movement model, you generate a range of networks that can be the possible scenarios. You get a range of different scenarios that are possible. These networks should be put into a disease model, and through this disease model you can see where in simulations where the most outbreaks will be based on the network that you're using. So, yeah.
Any other questions? If not, thank you for the presentation. And then we move to the next presentation.